Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about what I call the power triangle. And the power triangle connects three major concepts with us in chemistry. It connects electrochemistry to thermodynamics to equilibrium by using these two equations. Now, if you're in an AP chemistry class, okay, these equations are on your AP equation sheet. If you're in college chemistry, hopefully your teacher gives you these equations, because if they don't, then they are going to be ones that you're going to have to memorize. But they do connect three major topics of electrochemistry, thermodynamics, and equilibrium. In the last problem that we dealt with a voltaic or galvanic cell where the calcium is being oxidized and losing the electrons and giving those electrons to aluminum. Now, the calcium can't give up 2 electrons and have the aluminum receive 3, so we had to do some multiplication. We multiplied this by 2, so it's receiving 6 electrons, and of course we had to multiply this by 3 so that it'd give up 6 electrons, and then when we put everything together, these two equations, you can see that 6 electrons are going to be lost and 6 electrons are going to be gained and 6 electrons are going to be lost, which means 6 electrons are being transferred from the calcium to the aluminum. Okay, now those number of electrons that are being transferred are really important because that's going to be the N in this equation. Okay, now in this problem, okay, between calcium and aluminum, the standard state potential is going to be 1.21 volts. And what we can use is we can use this number of 1.21 volts to figure out the delta G for thermodynamics and then figure out the K for equilibrium. Okay, so let's go ahead and take this number and figure out what delta G is by using this equation. So delta G is going to be equal to negative NFE. Okay, well, the number of electrons that are being transferred, I stated, was 6 electrons. So N is going to be 6. The Faraday's constant is 96,485. And the E cell is 1.21. And when we put all that together, we're going to get this number of negative 700,481. And that's going to be in joules. Okay. Now, as far as the units are concerned, this is going to be moles of electrons for the N. Faraday's constant is going to be coulombs per mole of electrons. So you can see where the moles of electrons cancel each other out. And this is going to be in the unit of volts. Okay. And if you look at what a volt is on your AP equation sheet, you're going to find out that it's equal to a joule versus a coulomb over a coulomb. So this volt is actually joules over coulombs. The coulombs cancel out, and that's how I'm left with the unit of joules. Okay. Now, one thing that I want to point out, okay, when you're doing electrochemistry, if your E cell is positive, that means the reaction is spontaneous. That means this reaction will work all on its own. No outside factors are needed. It just occurs naturally, spontaneously. College Board likes to call that thermodynamically favorable. Okay, and when E cell is positive, it gives you a negative delta G. And remember, from our thermodynamics unit, a negative delta G means the exact same thing. It means the reaction is spontaneous and it will occur. So for electrochemistry, E cell has to be positive, but in thermodynamics, delta G has to be negative in order to say that the chemical reaction will occur all on its own naturally. Okay. Now, if we want to connect that to equilibrium to figure out the equilibrium constant for this reaction, okay, we would use this equation. Delta G is equal to negative RT natural log K. So if I want to figure out the equilibrium constant, okay, I'm going to have to divide by negative RT on both sides of the equation. I'm going to plug in my delta G as negative 700,481, and that's all going to be over negative 8.314 for the R. And the temperature, we're going to say, is at room temperature, which is a standard condition. And if it's at 25 degrees Celsius, that means it's at 298 Kelvin. And when I figure this out, when I take negative 70,481 and divide it by negative 8.314 and 298, I get this number of positive 282.7. Okay, and I get that because these negatives cancel each other out. And all of that is equal to the natural log of K. Now, if I want K is going to be equal to e to the 282.7. And for a lot of you guys, when you plug that into your calculator, it's going to give you an error because this number is just too massive. Okay, I believe most of those graphing calculators, when you get into exponential notation, it'll do times 10 to the positive 99, but I don't think it goes over 100. And obviously, 282.7 is a number over 100, so I don't even think your calculator can handle it because this number is massive. It's just too big. And if I want to remind you anything about equilibrium, when the equilibrium constant is really, really big number, like this number that we have here, that means that this reaction favors the products almost 100%, which means once again, we're in agreement that this chemical reaction is going to occur. Okay, so when this is positive and this is negative, this number is going to be a super, super, super big number. And all those things, that means that the reaction will occur. Okay. Now, the opposite is true as well. If you get a negative E cell, that means the reaction won't occur. Of course, that will give you a positive delta G, which means the reaction won't occur. And then your K value, instead of being really, really big, it will be really, really, really small, which means it completely favors the reactants and the reaction doesn't work. Okay. So if you found this information helpful on how to connect electrochemistry to thermodynamics to equilibrium, please give it a like and subscribe. And when you leave a comment, it really does push the information out to other students that might be interested in learning chemistry.